All right, class, we're going to get started. So today we have lecture 2, which is really is going to be a much shorter lecture than our previous lectures were. So we're basically going to look at some more examples of where we would use statistics, almost as a preview of some of the things we're going to be doing over the rest of the semester. We'll talk a little bit more about Python. Python was embedded in the lecture notes 1. They'll be embedded in all of the lecture notes. It's part of your homework. We'll talk a little bit more about some of the functions that are available in Python for you to use. And go through some examples of some questions that we'll be able to answer with statistics. I guess one thing about today's lecture, I'll just give you forewarning. We're not going to get, in this lecture, we're not going to attempt to get all the way to the answers in the 3 examples that we pose here. So we're going to have to develop more tools, right? In lecture 1, which we went through last week on Monday and Wednesday, we started with a question, right? How do we determine the probability, or how do we determine how unlikely it is that we would see 6 cancer cases on a block of 120 people? And we went through some general rules of probability, and we developed or the binomial distribution, then defined the binomial distribution, and talked about the mean and variance and so on of that distribution. So we developed a set of tools to answer that problem. Today, we're going to introduce 3 additional problems that we are not going to develop all the tools for in today's lecture. There's too much to cover to get to the answers to these questions. But these are kind of the previews of the types of things that we will be working on in this class. And also we'll show how we can kind of get into that work in Python. But as I said, it's a shorter lecture today, so we're going to have more time at the end. I know there's a lot of questions on the homework. A number of you came by office hours today. Thank you. There will be, but I was unable to get to everyone's questions earlier. So hopefully we'll be able to get to that. We can also answer any other questions we have on lecture note 1 or other material today. So we should have time for that. But before I get started, any questions? So we'll talk about the homework, I think, towards the end of this lecture. But are there any other questions before we get started? Okay. Right. As a reminder, we have our first quiz in class on paper on Wednesday. Okay. So, all right. So some other examples of why statistics is useful. So this book, The Cartoon Guide to Statistics, I should have brought it with me. I've actually recommended this to some of you who came to my office hours earlier. I think it's a really nice and clear guide, visual kind of guide to some of the concepts in probability and statistics that we're going to go over in this class. It's not a textbook, so it's not priced like a textbook. The version I have, it was published in 1993, and the version I have was handed down to me from the previous instructor. It might have been printed in 1993. It has a list price of $15. I'm not sure where it is today, but it's a useful. I think it's a really useful reference or supplementary reference for a lot of the material that we'll be going over in this class, especially in these early probability bits. But that cartoon guide says that statistics and probability help to make good decisions in the face of imperfect information and real risks. And what makes statistics unique is its ability to quantify uncertainty and to make it precise, or allow us to make precise statements. This allows statisticians to make categorical statements about their level of uncertainty. All right. So again, at the beginning of the first class, I mentioned that we start with probability because all of our statistical estimates are going to be probabilistic. And what this is basically saying is that the reason statistics is probabilistic is because real data, real life, real situations we encounter have uncertainty. And so probability and statistics give us the tools to handle that uncertainty and make more certain statements about how uncertain we are, if that makes sense. So that's the kind of question that we'll be able to address. So one example would be, let's say we have, we're taking measurements of air pollution emissions from industrial facilities where each measurement that we make is very expensive, right? So we can't just take a lot of measurements. We'll see actually in a lot of statistical problems, if we could just collect more data, things generally get better. Like we get better estimates of anything we're trying to measure if we just collect more data, but often we're limited by time or money or other resources, like people available to go take that data. And so we generally have limited data to work with. So let's say that we have the permitted emission rate of some pollutant of 75 kilograms per hour, and our team goes in and measures 3 values, 72.7, 73.9, 74.2. All of them are below that limit, right? All of them are below that critical limit of 75. But how, from this though, what would we estimate is the actual emission rate, and how uncertain are we, right? How likely is it that the emission rate is actually greater than that 75 kilograms per hour, right? So we made 3 measurements that are all below it, but kind of close, right? Let's say maybe uncomfortably close to that limit. So what's the probability that the true emission rate is actually greater than that? And we just didn't, maybe we just came in and sampled it. We got 3 really good samples, right? This comes from a problem in air pollution control engineering. Second problem that we'll just start to get into and show how to start to get into in Python today is about air exchange rate in a well-mixed room. We'll say that we can find the air exchange rate in a well-mixed room by putting in a pulse of a stable gas as a tracer and measuring how that concentration decays in time. And we're going to be given some data, which is down here. Time in hours, 0 through 5 hours, and the measured concentration at those individual times, right? And from this, we want to compare to a model of what that tracer flux looks like over time, and try to figure out what the inflow rate is, right? One of the parameters in our model. So we want to use data to estimate a parameter from our model that in this case represents the inflow rate into this room. This comes from a problem in environmental engineering and science, this textbook here. And so here's our data. You can note that we've already started with Python a bit, right? So this important NumPy as NP, that's going to be, for those of you who stuck around for the installation of VS Code at the end of the last lecture, or if you watched it online, it's on YouTube. We're going to often be using NumPy, often imported as NP. That'll be our default. And then in this case, we're also importing Matplotlib as plot. So we have this library of tools, basically based on MATLAB, to plot the data. And then with that, with NumPy, you can see we've imported this data, we've written this data in as arrays, as NumPy arrays. And apologies, I mean, this may be, some of you may have no problem with this, but for some of you, this may be new. So we're putting these in as these NumPy arrays with this syntax here. All right, and then problem 3, before we get into just baby steps into these 3 examples. Again, we're not going to get to all the full examples today. Would have to do with process engineering. So let's say we have, we're at a manufacturing plant, and there's some standard method A and some modified method B to make batches of, to make a particular chemical. Let's say, so what we're measuring, what we're going to look at is the yield of method A versus method B. And your task as the intern at this company to try to determine, is method B, this modified method, better than method A, right? Do we get better yield with method B than we get with method A? And this is the data that we see here. So these are the actual measurements that you get for yield from batch fabrication of this chemical. And so we'll look at starting to address this problem using some of the tools that we have. But again, a final answer we were not going to get until later in the class. All right, and again, you'll note just for the Python piece that we've put these in as these NumPy arrays, is the syntax that we're using. So let's start with our example 1. So we have these air pollution emissions, and we have 3 measurements, 3 very expensive measurements of air pollution emissions from a facility. And we want to know if these air pollution measurements could have possibly come from a facility that is actually generating a pollution at greater than some specified threshold, right? It could be some set by some federal emissions limit or something. So we'll just start by calculating the sample mean, right? So this is our expression for sample mean for data from an unknown distribution when we have real data. And it's just going to be 1 over n sum of the values times the sum of the values, right? I don't know, I guess you've probably seen this as average previously. We're being a little bit more specific to say that the average we mean here is the mean, because we'll also describe the median, for example, is the 50 percentile value is another way of describing the center of a distribution of data. But here we're going to talk about what we're computing first is the mean. So to do that in Python, we're going to say, and define a variable as a NumPy array containing the 3 measured values. I'll note here, comments are really important. Comments, in particular, whenever you put a value in that has units, just put the units as a comment behind it. That's really good practice to get into, just so you know what that number is. And so we're using here a comment. We're saying this in kilograms per hour. And then we can put that formula, that equation 1, we can represent that in Python as by saying the mean stack is just the sum of values in this NP array. That's what this executes here, divided by the length or len of that array. Okay. And so then we print that out and we get 73.6 kilograms per hour, which again is lower than the the specified emission rate, but we don't yet have the tool to say if that is acceptably lower. We can also do this by defining a function. So we define a function called myMean of x, and it's just going to return the sum of x over the length of x, where x is a NumPy array. And if we use that, we can then print this out as this myMean of that stack NumPy array, and we get the same answer. Okay. So apologies to those of you for whom this is a basic review of Python, but I know that's not true for everyone. We want to make sure everyone's on the same page. Okay, cool. Yeah, I see some nods. I see some people, I think, maybe frustrated at how slow things are going, but I see other people, I think, hopefully happy that things are going fast. Or actually, where do you all stand on this? I should know. Is this something you need? Is it useful for me to go very slowly through the Python? Yeah, okay. Okay, so then we're going to keep going at this pace. And if there are questions on this, honestly, on the Python piece, let me know. Also, your TAs are a great resource for Python, and there are a number of resources that are called out on the Canvas page as well. Okay, so we can define a custom function. This would be useful if we have to do this mean a bunch of times. But as you might expect, there's also a built-in function in NumPy to do this for you as well, right? So you don't necessarily have to write your own function. We could also say we could find the mean of the stack data using the function in NumPy np.mean. And again, we're going to pass in that NumPy array. And when we do that, right? So this is the mean via NumPy, right? Via the functions that are available to us as part of that NumPy library. We're going to get out this same value, the 73.6. Okay. So 3 ways of doing the same thing. So very similarly, we have the sample variance. Right on your homework, if I was asking for the mean of an array of numbers, any of those is fine. Okay. I'm not going to require that you use NumPy specifically. So any of those methods to compute this in Python are totally fine. So again, for sample variance, we defined sample variance in this way. Remember, this is n-1 is our estimate is what we use for sample variance, because this allows us, when we have a sample of a select number of data points out of some larger potential set, we always use this n-1 in the denominator instead of n, right? If on the other hand, we had, let's say we have something finite, like there's only 120 possible values of something that we are sampling from, and we know all 120 values, and we want to find the variance of that entire population. We know all the values in the population, and we want to find the variance of that entire population. Then we lose that -1 in the denominator here. And if you remember from lecture 1, we said that that's because otherwise, when we're computing the sample variance, we're doing it relative to the sample mean. That sample mean is always going to be closer to the values in our sample than the true mean, right? The true mean of the whole distribution. And so by using n-1 in the denominator here, we account a little bit for what would otherwise be an underestimate of the sample variance. If that makes some sense, maybe. Okay, no feedback. So does that make any sense at all? Why we use n-1 instead of n? Because remember, we had two different formulas for variance, depending on whether we have the population or the sample. And it's a subtle point, but in this case, actually, the difference is pretty large. Yeah.
Like, in what context are you going to use the sample mean versus the population?
So if you had all values of the population, right? So yeah, if you had all possible values of a population, like let's say it was, height of just this class is the distribution that we are interested in, right? Then we could go and measure the height of every single person in this class, know all of those values, and then the variance of that distribution, right, of that entire population would be 1 over n, the sum of all those individual values minus the mean of the entire population squared, okay? But now if I tried to estimate, let's say I didn't want to actually make all of you stand in front of a tape measure or something, right? And I said, well, I'm just going to, instead of measuring 50 heights, I'm going to measure 10, right? So I'm going to take a sample of 10. So now I only have 10 values. I have a sample instead of the full population, okay? So I have 10 xi's. I would then compute the sample mean, right? We might denote it as that lowercase x bar, right? Just for those 10 values. Now that sample mean, let's say that I happen to sample like mostly students towards the shorter end of the distribution within the whole population, right? My sample mean is going to be a little bit smaller than the actual population mean. So all of these numbers here, right, are going to be a little bit smaller than they would be, right? These distances to the sample mean are going to be a little bit smaller than the distances to the actual population mean. And so I'm going to be underestimating a little bit. And so instead of dividing by n, we divide by n-1. And that accounts for what would otherwise be the underestimation of the variance. Makes sense? A little bit of sense. So the exact reasons why it's n-1 and not n-2 is another question. But there's, and that's where we get into degrees of freedom and so on. But just the fact that it has to be, that we're always underestimating. In the sample, if we were using n here, we would always be underestimating the sample mean. Sorry, the sample variance. Okay, so that's our sample variance. Here we have our sample standard deviation. It's just a square root of the sample variance. And again, note that we normally write variance as something squared, right? In this case, sample variance is write as little s squared because little s is a sample standard deviation. So again, we can go through and we can define a function in Python to calculate the sample variance and standard deviation. Right, so by just using that def command. One thing to call your attention to that you should be aware of in most programming languages, I believe, we tend to use braces or parentheses in order to indicate groupings of, for example, if we want to have a function definition, we would put an open parenthesis or an open bracket at the top and a closed bracket or something at the bottom of the function. In Python, we don't do that. In Python, these indents are really critical for how you write your code, and will change entirely how that code is interpreted. So the same goes, for example, when we have a loop, we don't have a loop here, or an if statement or something. If we have our text indented, then Python interprets it as being inside of that loop or inside of that if statement. And if it's not indented, then it doesn't see it as inside of that loop or inside of that if statement. For me, coming from years of programming in MATLAB, this is something that I find really strange, because it doesn't matter how much indenting you do. I learned in C++. There, it doesn't matter how much you indent. But in Python, it very much does matter. So here we can see that we have this function definition. Everything is indented past that function definition. Right? So we hit tab on each line. And then Python knows to interpret that as all part of that function definition. Does that make sense? So in this case, we have defined this function, my variance of x and the mean of x. So it asks us to put in x and also the mean of x. I guess we could have computed the mean ourselves within the function, but in this case we didn't. And then we just plugged in the formula for the variance. Again, it's going to be x minus x mean times x minus x mean over the length of x minus 1. Where here we're using a symbol for multiplication of all the individual elements within those array together. Okay. And multiplication and sum of all the variables within that array. And then our standard deviation we return as the square root of that variance. Yeah, go ahead. We'd have to make a loop. We'd have to loop over all the elements. Yeah, so we could have done this with a loop and then looped over all those elements. I'm not confident enough yet in my Python to do that live for you in front of class, but we could have done that as a loop. Yeah, I'll get there. Yeah. And then this is going to return two variables, the variance and the standard deviation out of that expression. And then we're using that, right? So we're saying the variance is my variance of this thing. And then we're going to print var s, the 0th element, the first element in that array, and then this the second element within that array. Keeping in mind that we're indexing starting at 0. So in this case, say the variance and standard deviation, 0.63 and 0.794. Again, we'll note that there's a built-in function in NumPy that we can use to do this. So we can use this np.var function. In this case, it takes in the our array, which we stored in stack, right? That has our 3 values that we pulled out, that we measured. And note that we do have this second argument here, which is the number of degrees of freedom, or the delta degrees of freedom. So the difference between the number of values in the array and the actual number of degrees of freedom. So in this case, we're setting DDOF is equal to 1. This is critical when we're computing the sample variance or the sample standard deviation. And actually, if we were to run this with without that argument, you see we get an underestimate of the variance in the sample, right? So so the default here is that delta degrees of freedom is equal to 0. The default of np.var is to compute the variance. I'll get you 1 second. To compute the variance of the population, not the variance of a sample. So we have to put back in that DDOF is equal to 1. In order to get the proper variance for the sample. Yes.
I just make sure that the validity of freedom, we're doing that equal because it's a sample population.
That's correct. That's correct. So we have this DDOF is equal to 1 as an argument into np.var because it is a sample, not a population. If this were population data, we could either put in DDOF is equal to 0 or just omit that entirely, omit that argument entirely, and the default is DDOF is equal to 0. That's the default behavior. Yep. Yeah, definitely. Yeah, so question is on the homework, so you're allowed to use these built-in packages? Yeah. I mean, that's why we're showing them to you here. So you don't have to reinvent all these things yourself. Yep. So on the quiz, will you have to know how to do the functions by hand? No. The quiz, you will have to know the concepts, but I'm not expecting you to write Python, handwrite Python code. I'm not going to do that to you. No. Yeah. So I'll give you a list of formulas from lecture 1 will be the formulas that will be relevant on quiz 1. And so you'll have those as part of the cover sheet for the exam. Yeah. Yeah, because remember, again, it's closed book, closed notes. Okay, other questions? Yes.
So,
Yes.
So why is there so much difference in the variance between doing the population?
Because we're doing 1 over square root of 3 versus 1 over square root of 2. And that is a big difference. Yeah, so most of the time, if we have so I'll say this, most of the time when we have a large population, right, if we have a large sample, the difference between 1 over square root of n, 1 over square root of n minus 1 is not that big. But when we have, it's especially amplified when we have a very small population, or small sample, sorry, small sample. Yeah, okay. Other questions? Yes. When we start doing t-testing, definitely, when we start asking, actually, the next step of this is that we're not going to get into today. Once we have these numbers, we would then have to do some kind of a statistical test to determine how likely it is that our mean is actually less than 75. That's a t-test that's using a different type of distribution, and there we're definitely going to encounter higher degrees of freedom. But yeah, we're not there yet. Other questions? Okay. Okay. So here we have, where were we? So here, just another way of doing this is with our, so we're using the standard deviation, sorry, np.std, standard deviation gives us the standard deviation of the variable. Again, note that we have delta degrees of freedom equal to 1, because by default, the NumPy standard deviation function uses delta degrees of freedom of 0. So by default, NumPy is computing the standard deviation of a population, not a sample. Okay, so same caveat applies. Okay. Another way of finding this, so we could store variance. We go back up here. We stored variance as the output of the NumPy variance function. And when we do that, if we come down here and we just we know that the standard deviation is the square root of the variance. So if we computed the variance this way, we could then find the standard deviation as the square root of that value. And again, get the same thing. And actually, I'll show you one more thing just to be aware of. So we typically, so when we're working in one of these Jupyter notebooks, we'll often be going through and evaluating things cell by cell. And you can go through and make it recompute everything for you. But by default, a lot of times it's convenient to not do that, especially if you have a lot of data. Let's say I go back in and I get the wrong answer here, right? So we have a sample, but I use the formula for a population. So now I have the wrong value for variance. Down here, this expression depends upon that variance, but because it's in a different cell and I didn't execute this cell, I haven't updated this number. That makes sense? So when you're checking your answers and you can't find an error, sometimes it's helpful to just rerun the whole, rerun all the code. But now if I go down here and I update this, I'll get, again, this is the wrong answer for it. And then maybe I go back in and realize my mistake and I set this back to 1. I still have the wrong answer down here because I haven't rerun this cell. And I'm just doing Control Enter to rerun that cell. Okay. So what we can say so far, so we can't yet say something about exactly whether or not or how likely the mean is to be below that 75 kilograms per hour limit. So we're not there yet. We're going to need some additional statistical testing in order to be able to make a statement about that. But we can say that we can state some expectations about what we expect the range of values to be that we would see based on the mean and standard deviation. So for example, we said last time that for normally distributed data, and again, we're going to talk about normal distribution, but we generally expect to find about 68% of values between the mean minus the standard deviation and the mean plus the standard deviation. And so we would expect that at least the values that we sample, roughly 70% are going to be within this range of 72.8 to 74.4 kilogram per hour. But we can't yet say if that means or how confident we are that this particular facility is underneath our 75 kilogram per hour limit. We're not there yet. Okay. Any questions on that? Example one, we went through exhaustive. We went through Python in a few different ways, right? And a few different ways of answering the same question, more or less, using Python. And we're not yet at the statistical testing, but we will get there. Okay. So ultimately, we're going to want to make a probabilistic statement about how confident we are that the facility is not actually routinely exceeding the 75 kilogram per hour limit. But again, we'll develop those tools. Okay. So example two, just scrolling back up to remind ourselves of what example two is. So we have air exchange rate. We're trying to find the air exchange rate in a well-mixed room. And we have measured the concentration of a tracer, some kind of stable tracer molecule in that room as a function of time, right? So we have this data defining those two things. And now we want to know, and what we're eventually going to want to do is now compare this to a model in order to find that injection rate I. So this code here is using that matplotlib, which again, remember, we imported as PLT. Right? So we imported this to Python as PLT to make a plot of the tracer concentration as a function of time. So in this case, we gave ourselves a flag here. This is what we call this. We call it, where'd we go? We call this flag. So we had this flag tells us that we don't want to save the figure, but it gives us an option to save the figure later if we want to. We've written that into our code. Then we say we're going to define a new plot with time and ppm, so x and y. These options tell us that we want it to be red with dots at every individual point and lines between them. That's what that RO dash means. The title is tracer concentration, so we're going to put a title on the plot. Here's our Y label and our X label. I guess we don't have, we have units of ppm, units on both, which is nice. And then we have this if statement, again, that's telling us that we're going to, like, if that saved figure were set to true, then we would actually save a JPEG of that final figure. And then finally, we have an expression to show the plot. So actually, this is another example of that indentation meaning something in Python. So instead of, again, other languages, if you may have seen something previously, you might have an if and then an end at the end of an if statement in order to define the stuff that's inside of if. Or again, you might have brackets or something. In Python, we don't do that. In Python, we just have this indentation. And so this is all part of that. So if I actually put this into the if statement, then that plot would never show. So I have to actually take it out of the if statement by just removing the space. Removing the tab. And then when we run that, we get a plot of the data, the tracer concentration function of time. Any questions on that? So that's matplotlib. We'll be using that. It's a convenient way of plotting, making plots in line in your Jupyter notebooks. Yeah. No question. Got it. If we want to understand this tracer data a little bit better, just to think back to maybe intro to Chemie, and universal balance equation. So if we just look at balance of material in and out of some box, then we can start to develop, sorry to bring back painful memories maybe for some of you, but we can look at the concentration of that tracer within the box by saying that the rate of change is going to be rate of transport in minus rate of transport out plus rate of generation minus rate of consumption. Here we're just defining all the variables in that expression. The emphasis here is really not on derivation of this kind of thing, but it's on how we can interpret models using statistics. So we're not going to dwell on this. But by applying that, we can develop governing equations from that balance equation that we would use then to determine I, where we now have the concentration written as a function of that variable I. So once we have this, right, so we'll say in other classes, you'll be developing equations that describe processes that we might be interested in learning about. And now if we want to actually use those expressions to make measurements about what's going on in the world, we're going to collect real data. And then we can do things like curve fitting to that data. So we can then say, let's say for our plot of tracer concentration versus time, we can then fit this to a model and then make a statement about what that variable I was, for example, that we were trying to measure with this. And then because it's a statistical measurement, a probabilistic measurement, we'll then be able to make statements about uncertainty, like how likely is it that that value is within a certain specified threshold, for example. Okay, any questions on that? Less coding, more plotting so far, but we'll get to that. Example 3 is the case where we're comparing treatments A and B in some chemical manufacturing process. So again, remember we had some list of yields for process A, and we're comparing it to measured yields for some new process B. And you, as engineering intern at XYZ chemical company, are tasked with determining, is process B better? Do we get better yield with process B than we got with process A? And so the first thing that you might do is just take that data and compute the means, right? So here we're just using the numpy.mean. We could have used our function or defined the function explicitly, but we're just using the mean, and we're taking the mean, and we're using numpy.mean, and we're taking the mean of the yield data that we had for A and B. And then we're defining another variable as the difference between those two, because we want to know how much bigger or smaller is the mean of B minus the mean of A. And then we're displaying all of that using the print command. Right, so here's the output of that. And we can see that the mean of A is 84.24, the mean of B is 85.54, and the difference is 1.3, right? So the naive first answer before statistics, right, before we understand how to deal with the data is, well, B is higher, right? Therefore, B is better, right? But that ignores any information we have about the variability within those two data sets, right? So we need tools to understand, like, is this significant, right? Yeah, the mean is higher, right? It's 1.3 higher. But is that actually meaningful, right? Can we actually say that from the data that we collected that process B is better and that the plant should switch over to process B because yield is going to be higher? And so statistics will give us the tools to say that. But one thing that might be helpful just to start with is to note that we ran just over time, we ran 10 treatments of A followed by 10 treatments of B. So maybe sometimes just plotting, visualizing the data is going to be something that we talk about as well. So it can be helpful to just plot them in order and see if there are any trends. And so we're going to take those data and we're going to put them into a new array, a new NumPy array, that is the concatenation, basically just taking the one array and glomming it onto the end of the other array of yield A and yield B. Right, so we're just going to put it all together, stick it all together into one big long array. And then we're just printing those values. So here we just printed those values, right? And then let's say we know the timing of it. They were taken every, 1 hour, minute, or something. So now we define a t variable using np.linspace. So we could define t, right? We could just go through and say t is equal to 1, 2, 3, 4, 5, all the way up to 20. This linspace command, however, lets you do it a little bit more easily, but just based on, for example, the length of the, so you define, for linspace, you define the first value in your array, the last value in your array, and the number of values that you want in your array. And so in this case, it's just 1, the length, and then again, the length, and we end up with this array of 1 through 20. And then again, we're going to plot them. So we're going to make another plot using matplot library. In this case, we're using a slightly different format. So last time we used this kind of condensed format where we said R, O, and dash to make our plot and define our line style. Here we're being a little more explicit, which is another option we have. We're defining the color, the marker shape that we're going to use, whether that marker is filled or not. So these are going to be open because we said fill style was none, and whether or not there's a line. In this case, line style is none. Here we're putting a treatment, a Y label, an X label, and then we have this plot.show, which we always need in this matplot library. And this is what our data looks like if we plot it in time order. Remember, the first half of these are from method A, the second half are from method B. We know the mean with method B is a little higher, but I'm no longer, from looking at this, I'm not so confident that method B is better than method A. But with statistics, we'll be able to then describe with more precision whether method B is likely to be better than method A from this data. All right, so there's a difference in mean, but is it sufficient to show that one is better than the other? To be continued. Yeah, I will keep this recorded. Yeah. Okay. So questions. I have a question here in the front. Yeah. What's that? Yes. So first question is, how do I expect you to do the homework, Markdown or Python? It's actually a mix of both, right? So some of the problems are going to require Python code. Some of the problems would just be done in Markdown.
Okay.
Yeah, interesting. So the question is, I'm just repeating for you to do. The question is, if you can do it the long way, would it be graded down? Yeah. Yeah, so I'll say no. You will not be marked down for that. And I told the TAs to grade pretty leniently because the homework. So my philosophy on homework is that your homework is more practice of the concepts and getting some familiarity with Python because that's another goal in this class. But I don't want them to be too, and it's only 10% of your grade. I don't want them to be too harsh on it. And I'll make sure they know that yeah, there are many ways of getting to the same solution, and it doesn't really matter which method you use. That said, I think you're probably better off doing it in Python, because it'll be faster in the end. I know you have to learn Python. You're gonna have to learn Python eventually anyway, in this class to get to the later homeworks. So I think you're better served doing it using the tools that we talked about in class. and just diving into it now. So that way later, when you have something that's more complicated, you don't have to also learn Python and do the more complicated thing. Does that make sense? So maybe not the answer you wanted, but yeah, if you do it another way. So, for example, in today's lecture, we went over how to compute the mean, and I guess we did it a couple of different ways. Any of those ways would be fine on the homework, right? So define your own function, you have an inline function, or use the built-in and NumPy function. All of that's fine. Okay. Okay. So the next question was how to approach problem 6, right? Okay, let's pull up problem 6. Yeah, so this is the case where we have these two processes. We know mean and variance of those two processes, and now we want to find the mean and standard deviation for the two together, right? So we just have it's coding process followed by a rinsing process. So how do I find that, right? And so we have a coding process. We know the mean is 35 minutes, the variance is 11, right? And then we have a rinsing process, mean of 8 minutes, variance of 5. So if I run one trial of coding, then rinsing, how do I find the total time? What I'm interested in now is the total time. How do I find the total time? It's not a trick question. Add them together, right? So I take so if I have a single trial of coding followed by rinsing, the total time was the time for that first coding plus the time for the second rinsing, right? So here I'm not talking about individual trials, but I'm saying that I know that the coding on average takes 35 minutes. And the rinsing process on average takes 8 minutes. So the first part here is what is the average, on average, what is the total time for the combination of the two processes? Does that make sense? This is one where I think you know the answer, probably. We gave an explicit form for what that is. We talked explicitly about how to find that for linear combinations of events in lecture 1 notes. And in particular, you probably need to look at those to figure out, like you're asked to find the standard deviation of the total time. So I suggest you go back to the notes in order to figure out the standard deviation piece. I'm guessing you could guess the mean bit, but you should go back and make sure you look in your notes about the standard deviation piece. Then talk to your TAs. Okay. So a follow-up question on that, and you were first, Jeff. Mm-hmm. So that's if we have something like AX plus B, or let's say we have some processes where it's like AI, A1, A2, A3, and whatever, right? So in this case, what's the value of A1? A1 is 1. What's the value of A2? Just 1. What's that? It's 1 because the formula, our expression for the total time. So can someone tell me, so what's the expression for the total time of the process? So the time for the process is, we're going to say in general, right? So the total time, it's going to be our sum of AI times the time for the individual i's, right? And then our expression, so what's our expression for the expected value of the time in terms of all of these AIs? So the expected value of the total time, someone tell me, what's the expected value from lecture notes 1? So if I have some process where I have the sum of, where I'm just taking the sum of a number of different processes with some weights I, or AI, how do I find the expected value or the mean? Sorry, that's not sum, that should be E. The expected value or the mean of that total time. Any help? Let's go back to lecture notes 1. So go down. So let's say, so I have the expected value, looking for a cleaner writing of it. Here we go. So we have some linear combination, right? I just wrote that as capital T, but it's at capital Y, A1x1 plus A2x2 plus all the way up to AKxk, right? In this case, K is 2, right? Because I just have two things that I'm adding together, right? The rinsing time and the coding time. What this tells us down, so when I write all of that out here, I get down to the result that the mean of Y, right? The mean of the sum of all of these things multiplied by those weights is just the sum of the weights times the mean of all the individual processes. That makes sense? No. Yes. So the A is like a weighting that's being applied to some random variable X. Right. So, let's say we could modify this problem and say that the rinsing happens twice. Right? Let's say we need to rinse twice. Then that weighting of A for the rinsing process would be 2, right? Because we would do the rinsing twice and the coding just once. In this problem, it's just 1. It's not always going to be 1. Yeah. In this case, we're just taking the sum of these things, so it's just 1. Does that help a little bit more? Yeah.
What is the mean of the individual value?
So we have, these are, so if we have, in this case, we're looking at a linear combination of some weighted set of random variables, xi. In this case, our random variables are the amount of time it takes for the coding and the rinsing process. And the weights that we're applying to them are just 1 to both processes. This is telling us that we can find, an individual value of that combination, that linear combination, as as a sum of AI xi. And it tells us that we can find the mean of the sum of the linear combination of those random variables as the sum of AI times the mean of the individual variables. That makes sense? Let's go back to the homework. So if we look at the homework, what that means, so we have the coding process, the mean is 35 minutes. The rinsing process, the mean is 8 minutes. So my total time is coding plus rinsing. And this is telling us that on average, the total time it takes to do one coding process plus one rinsing process is going to be, what do we get? 42. Yeah. Okay. What if we had to do the rinsing process twice? What would we get? 50. Right. Then the weight for the rinsing process would be 2. And if we plug this in here, right, so we have expected value of that process, of that total time t, is the sum of I times, we'll say expected value of ti. And so if we had to do the rinsing process twice, then we'd end up with 35 plus 8 times 2. Okay. Yes.
So basically the thing is that
Mhm.
instead of how to like the mean of y, you can just look at it as if you already know what
Yes, that's exactly it. Yeah, so the reason we use this is instead of, like, let's say we know how long the coding process takes on average. We know the statistics of the coding process. We know the statistics of the rinsing process. And now we're asking, okay, we're in the plant, we're actually going to put these two things together, right? How long on average is it going to take, right? Or we know we're doing the coding process, and then we know we're doing the rinsing process twice. On average, how long is it going to take, right? Like, oh no, that still was not sufficient. We're going to have to rinse 3 times. How long on average is it going to take? Okay. So, and then the second piece is the variance, right? And, you know, there again, follow the lecture notes to find variance and standard deviation, okay, of that coding and rinsing process together. Yeah. In the variance, it gets squared. So this is the variance expression, because variance, again, has to do with the square. This comes in because variance has to do with the square of the difference between the values and the mean. So that's where that comes from. But yeah. Okay. Yes. A doesn't have to be an integer. Yeah, A could be any kind of weighting. Yeah, it does not have to be an integer. Yeah. In this case, it was just 2 processes, so it had to be an integer. But it does not have to be, in general, does not have to be an integer. Yeah. Okay. Good questions. Other questions? Yes. No, Wednesday will just be the quiz. Just the quiz. So the quiz will start at 3 o'clock. You'll have an hour. Okay. Yeah, good question. And you had another question on homework. Is that correct? It was that question. Oh, on the quiz. Okay, great. Yes. So the question is, will there be a study guide? How about I will give you the equation sheet before you get here, so you'll know what's on the equation sheet. Will that help? Okay. Satisfy kind of, yeah, I'll post it on campus. Yeah. Yeah. Okay. What else? Other questions? Okay. Can anyone help on how to approach problem 5? I'd much rather have everyone help than just tell you the answers. So how do we approach problem 5? I'll pull up problem 5. So here's problem 5. Go ahead. Yeah. Does that make sense? So you know, yeah, basically, like, you know what f is, right? And you can take the derivative of f with respect to x. Just go through, look at it, show it for yourself. It's not meant to be an overly involved one.
Yeah.
Next time, just get us started. Anyway, other questions on homework, or is that, or on problem 5? Let's start with problem 5. Other questions on problem 5? No, in this case, we're just saying that we have some, like, y as our function. Yeah. Other questions? Yes. Yeah, so how much do we have to do on this? This one does not require coding. This would be a markdown. This would be a markdown problem. Yep. You should explain. So yeah, there needs to be some explanation of why you got to here, how you got to that answer. Yeah. Yeah, I mean, it's like if there were to be a true or false problem, or like a yes or no problem on a quiz, most of the grade would be for telling me why, not just getting whether it was yes or no. Okay. Other questions? question is, do we have to have that much depth in writing? There should be enough depth in writing to, all right, this is squishy, but sufficiently explain your answer, right, and your reasoning of where you got that answer. Okay.
I guess that could make sense with her.
Okay. Can anyone else get us started on 5 in just a little bit slower? Let me get started on 5. Yeah. Actually, this is great. Yeah, I like this. Yeah. Let me give another direction. So let's say this is like saying, let's say our function f is a1 times little x plus a2 times little y plus a3 times little z. Then is this expression for the variance in f consistent with what you would get by plugging in that up above, that equation 34? So I would suggest starting there, saying this says that f is, let's say that f is a1 times little x plus a2 times little y plus a3 times little z. Is this consistent with this? There's some random variables that we have. Yeah, are the big X1, big X2, big X3. That's true. Okay. Start there, I think. All right. Other questions? Yeah. Yeah. So the question is, how many problems on the quiz? What will it look like compared to what we had on homework? So there's going to be no Python coding, but it will be concepts that you've used in your Python code on the homework, very much related to the types of things we've had on homework and that we talked about in lecture. So it will be similar. How many questions? I don't know exactly yet. So I have to, 60 minutes, that's correct. Yeah.